In this video, we are graphing rational functions. In a previous video, we did number 1. In a previous video, we also did number 2. But in this video, we're going to do number 3. But you did not see that coming. Okay, and the first thing I like to do is take care of my horizontal asymptote or slant asymptote. I'm going to say or because you're never going to have both. It's going to be one or the other. They are what you call mutually exclusive. So, it's all about the degree. The numerator has degree 2. The denominator has degree 1. Since the top degree is higher than the bottom, there will be no horizontal asymptote, so I can just go ahead and put none. However, if the top degree is 1 greater, then I will have a slant asymptote, unless the denominator cancels out completely, which is the one exception to that rule. But other than that, if the numerator degree is 1 more than the denominator, I should have a slant asymptote. So that's what I'm looking for. To find the slant asymptote, I will divide. Since it's just a simple x minus 2, I can do synthetic division. Be careful, this is missing the constant term. So if I do my synthetic division, the x minus 2, from that I'm going to put a positive 2 in the box. But for my coefficients, I'm going to do 1, 2, and 0 because of that 0. Okay, this is where the remainder goes. For slant asymptote, you want there to be a remainder here. If this turns out to be no remainder, if this is a 0, that means this is really a straight line. So let's see what happens. 1 times 2 is 2. That makes 4. 4 times 2 is 8. That makes 8. That's good. That means there is a slant asymptote. If I put the variables back in, this becomes x plus 4. That's why the slant asymptote will be y equals x plus 4. Now, the slant asymptote is a line. Think y equals mx plus b. So this 4 is the y-intercept of this line. And then the slope is 1 over 1. Okay? It's the coefficient. So I'm going to start at 4 because that's my y-intercept. Okay, so my slant asymptote is going to start off right here. Okay, and then because the slope is 1 over 1, that means my slant asymptote will go up 1 over 1 like this. Alright, so in fact these dots are so close together that I'm going to use these dots to go ahead and represent my slant asymptote. Okay, normally I make a dotted line or a dashed line, but this basically is a dotted line. I mean, it's literally a dotted line. Okay, so there's my slant asymptote right there. So what about a vertical asymptote? Yeah, boys. I will get a vertical asymptote by setting the denominator equal to 0. So if I take this x minus 2 and set it equal to 0, I'm going to get a vertical asymptote of x equals positive 2. So I might as well go ahead and graph that vertical asymptote right here. Alright, I wonder if you guys can hear me when the computer's glitching out like this. Alright, so I've got the vertical asymptote and I've got my slant asymptote. Now, what else am I going to need? Holes. Holes happen when there's a factor that cancels out. So to see if there are any holes, I need to try to factor this. the numerator will factor a bit. There's a GCF, there's a common factor of x. So I'll pull that x out front. That will leave behind x plus 2. In the denominator, I have x minus 2. Alright? The x minus 2 will not cancel out anything. So there won't be any holes. Nothing cancels out. So holes, none. Okay, so we can go ahead and do the domain now. Now the domain, when you look at the domain, if there are no holes to worry about, the vertical asymptote is all that matters. So for the domain is going to go left to right. So that means I'm going to start over here at negative infinity, and I'm going to go right up to the vertical asymptote. And then I'm going to hop over the vertical asymptote and do the rest of my domain to positive infinity. So I'm going to have two branches of my domain, one representing this yellow area and one representing the green. So this is negative infinity to 2, and then 2 to positive infinity for my domain. Okay, so negative infinity to 2, union 2 to positive infinity. I'm going to leave these parentheses round, showing that we are not including the 2, which makes sense because the 2 is an asymptote. The function will never actually reach the asymptote. Notice that I did not need to actually draw the function. It doesn't matter whether the function ends up being like here or here or here or here. It doesn't matter where the function is. The domain is still going to be the same based on the yellow and the green, based on the vertical asymptote. Now for the intercepts. Remember, the y-intercept is always 0, comma something, and the x-intercept is always something, comma 0. So that means if I want to find the y-intercept, I let x be 0. If I want to find the x-intercept, I let y be 0. Okay? So, looking at this function over here, remember that this f of x is like a y. Let's see if I can emphasize that. See this f of x right here? I'm going to cover that up for a quick second so that I can put a big old y right here. So this is like y equals. Okay, so if I want to find the y-intercept, I'm going to let x equal 0. So if I let x equal 0, that means I have 0 here, and I have 0 here, and I have 0 here. Okay? Putting 0 here, 2 times 0 is 0. So that means this whole term is 0. So really that means, let me make space. So I have 0 plus 0 is 0. 0 minus 2 is negative 2. 0 divided by anything is 0. Okay, so y equals 0. Alright, so when x was 0, then y turned out to be 0. So that's my y-intercept is 0, comma 0. So I might as well graph that right now. There's my y-intercept. Now look, this point is on the y-axis, but it's also on the x-axis. That means this point is at least one of my x-intercepts. There might be another x-intercept, but this is going to show up again as an x-intercept. Okay, just trying to make those connections. Now, anyway, we said if we want x-intercepts, we let y equal 0. So let's do that. So let me reset. Okay, so if I let y equal 0, that means I'm putting 0 right here where y is. Okay, so that means, so boom, there, here I'm letting y equal 0. In other words, I'm setting this entire equation equal to 0. Now if I do that, so I've got x squared plus 2x over x minus 2. Say I have 0 over here on the left side. That would be the same thing as having 0 on the right hand side. To solve this, I could multiply by the denominator. Okay, multiply by x minus 2 on both sides. Okay, these would cancel out. 0 times anything is 0. So that immediately leaves me with x squared plus 2x is equal to 0. Okay? Now, do you know how sometimes we say, look, for most functions, if you want to find the x-intercept, you can just set the numerator equal to 0. See how this is the numerator? And see how right here we have the numerator equal to 0? So it would be the same thing if I set the numerator equal to 0. It's just skipping one step. It's skipping the step where you multiply by the denominator to get to here. Okay? So look, if I erase all this, oh, look at that. I have the numerator equal to 0. Okay? I'm going to move it up higher though. So I have x squared plus 2x equals 0. So I got to solve this now. Remember how I had factored this a moment ago? I'm going to do that again. So pulling that x back out. So I have x times x plus 2. Okay, in factored form, because that's how I would solve an equation like this. I would factor it out, and then I would set the parts equal to 0. So I'll have x equals 0, and I'll have x plus 2 equals 0. That's how you solve this type of an equation. Now this is one solution right there. But if I subtract 2 from both sides, I get another solution. X equals negative 2. That means I have two x-intercepts, 0 and negative 2. Okay, so my x-intercepts are 0, 0, but also negative 2, 0. Okay, so two x-intercepts. So I can graph this second one, negative 2, 0. Okay, it's going to be right here. So those are my two x-intercepts. So fine. Alright, so let's go ahead and do the graph, and then we can do the end behavior. Okay, so let's just get some additional points. Now, here's my, I don't want to call it a pet peeve, or because I'm not angry or anything, but you guys tend to try to just do whole numbers all the time, or integers. You try to avoid decimals. I want you to cut it out. Okay, see the vertical asymptote? I encourage you to pick values that are just a little bit to the left and a little bit to the right of the vertical asymptote. So a little bit to the left of 2 is 1.5. I definitely want to see what's going on there. A little bit to the right of 2 is 2.5. I definitely want to check that out. So make sure you include these 2 points on your table regardless of whatever else you use. Okay, now focus on the vertical asymptote. I always want points to the left and points to the right. Okay, so I will also use like -1, for example. Not -1. Well, I'll probably wind up using that too, but I meant a +1 is over here, and over here would be 3. Okay, I'm just sort of going to the left and right. 0 I've already got, okay, but then I could do 4. Okay, -1 would be good to use, and I could do 5. Okay, and that fills up my chart, so this is a good amount of points to use. Okay, so I'm going to just put this function in my TI-30XS multiview. Okay, so what was it? X squared plus 2x over x minus 2. Yep. So there it is. I like to be in ask mode instead of auto when I make a table of values. So it's a personal choice. So my first three values are 1.5, 2.5, and 1. So I'm just going to type those in. 1.5, 2.5, and 1. Being in ask mode allows me to use as many decimals as I want. Okay, so at 1.5 I get negative 10.5. Now here I have found the rest of the values in the same way. So I'm just going to plot all of these points on the graph right now. Now 22.5 is way too big for me to fit on this graph. But the rest of these, I'm going to try to make them fit. Even the 15 and the 12, those are pretty high. But I think I'll be able to just stretch these out a bit. Maybe if I can get my hands on this, on the asymptote and like drag it out a little bit further maybe. Okay, I'm going to do this type of thing. So I'm just going to drag out my asymptotes a little further and see if I can make this thing happen. So anyway, I'm going to do that off camera and I'll get back with you. Alright, so here I've graphed the points as best I can. This one is a little bit off the graph. Okay, that's that negative 10.5 hanging out down here. So, but you can get the idea that there's a branch going in here. And then up here, I've got these 3 points way up high. Every single one of them is off the grid. But, you know, just do the best you can. You know, if I give you values that are off the grid like this, just estimate, just stretch out your asymptotes and just do your best. You know, I'll see that your table of values, that this is one of the reasons why we have a table of values instead of just plotting points by themselves. So now I'm just going to go ahead and draw these two branches, approaching the asymptotes and going through these points. Okay, this branch got a little sketchy in here, little bumps and bruises, but you get the idea. And I'm going to do the same thing up here as best I can. Yeah, I'm going to just let you watch me struggle. Alright, this is a little extra difficult with an electronic pen as I make excuses for myself. Okay, but it should be something basically like that. Alright, maybe I'll just zoom out so you can get the big picture. Okay, so that's basically what your graph should look like. Alrighty then, now we can do the end behavior. End behavior is what goes on the ends, meaning the left and the right. So understand that when we talk about end behavior, this is the left end over here, and this is the right end over here. Alright, we are not talking about what's happening here in the middle where the vertical asymptote is. Just those two yellow marks. That's it. So as we go to the left, this graph is just falling forever. So as we go to the left, the function is approaching negative infinity. Alright, as we go to the right, it's just going up into the sky. So as we go to the right, the graph is approaching positive infinity. Okay, so our end behavior will look like this. As we go to the left, the function is falling. As we go to the right, the function is rising. And that's it for problem number 3. That was our last problem.